Okay, so the last thing I want to define in this first section of chapter 6 is what's called the inverse Laplace transform. And so this would be similar to the relationship between integrals and derivatives, in the sense that we can think about the derivative as an inverse operation to an integral. So if we have a function capital F and there is some function lowercase f of t such that when I take the Laplace transform of f, I get the function I started with, then we would say that lowercase f of t is an inverse Laplace transform of f of s. So for example, just to write out something concrete, if I had f of s was equal to 1 over s, then what we'd want to find is what's a function when I take the Laplace transform, I get 1 over s. And then you could look at the table of Laplace transforms and say, I noticed that on the right side I found out that 1 over s is what we get when we apply the Laplace transform, for example, to just the constant 1. Okay, so therefore what I could say is that f of t equals 1 is the inverse Laplace transform of f of s is equal to 1 over s. Okay, so let's take a look at some examples. And when we take the inverse Laplace transform, I should say that we just denote this with the -1 to denote inverse operation. So to take the example that we had above, if I took the inverse Laplace transform of 1 over s, then what I would get is, in that case, 1. And so let's practice some examples of inverse Laplace transforms on the next slide before we kind of ratchet it up to look at some more complex examples. Okay, so here we want to calculate the inverse Laplace transform for several functions given in A, B, and C. And so on the left, I have my table of common Laplace transforms. And again, I would encourage you to have this worksheet out while you're working on problems from this chapter, since I wouldn't expect you to memorize these or derive them on your own. And so you'll see as you get more practice with this, you'll pick up on some of these patterns. So really what I want to do here is look at the structure of each of these functions, capital F of s, and based on what I see over here, we're going to reverse the process in the sense that I'm going to start in this column over here, try and identify which of these functions it most closely resembles each of these examples, and then we're going to work in this direction to identify what was the function whose Laplace transform gave us this. So if we're asked to calculate the Laplace transform, we start in this column and move this way. If we're asked to do the inverse Laplace transform, then we start in the right column and try and identify the function on the left. So if we want to look at 1 over s squared, and these are all of my options, this one isn't going to work, obviously, because I have just s to the first power down here. I don't have anything that looks like this in A, but now I do see that this one would have powers like s squared, s cubed, s to the fourth, and so on. So when I'm looking at 1 over a power function where the power is bigger than 1, then that's a pretty good indication that you started with the function t to some power of n. And so over here, if I've got s squared on the bottom, then this in particular must correspond to a value of n in this formula over here, therefore n would equal to 1. And this therefore tells me that 1 over s squared is actually the Laplace transform of 1 over of t to the first power. So in other words, the inverse Laplace transform of 1 over s squared is equal to t to the first power. I'll just put the 1 there. And we actually started, one of the first examples that we did was calculate the Laplace transform of t, and we got 1 over s squared. So now all we're saying is the inverse Laplace transform of 1 over s squared is t, since the Laplace transform of t is 1 over s squared. Okay, then in part B, we've got some constant 2 over s squared plus 4. And so it seems to resemble the sine and the cosine, but remember, for the cosine we have s on top, and for the sine we have b on top. And in our case, we have a constant on top, so it seems to line up a little bit more closely with the sine function. And in fact, it lines up perfectly with that sine function. What we can see here is that the inverse Laplace transform of this function f would give us the sine, in this case our value of b is 2, would be the sine of 2t. In part C, we don't line up perfectly with, say, the cosine, but it's pretty close. The problem here is that I don't have a 4 that I should have over here. So if I were to take the Laplace transform of the cosine, say, of 3t, then what this table tells me is I would get s over s squared plus 9. And I'm missing this 4 that we need. But remember that we know from properties of the Laplace transform, if I were to put a 4 inside of here, then it would just come out over here. Okay, and now we have a perfect match for capital F. So since applying the Laplace transform to 4 cosine of 3t gives me 4s over s squared plus 9, therefore the inverse Laplace transform of this function in C would be 4 cosine of 3t. Okay, and then for the last example, we are looking at f of s is equal to 2 over s plus 6. And what does that look like? So I can start to rule out some possibilities. So certainly it's not going to be one of these because we don't have s squareds on the bottom. S squared, this has an s squared. So it could possibly be one of these. This looks like something which is much closer to what we have over here. So in this case, my a is actually minus 6. Okay, so what that means is if we took the Laplace transform of e to the at, where again we said that our a was minus 6, using this table we can see that I would get 1 over s minus a minus 6, s plus 6. And the fact that we're just missing the 2, that's really easy to correct, because if we multiplied by 2 inside of here, then that 2 would just come out over here. And so therefore, since applying the Laplace transform to 2 times e to the minus 6t gives me 2 over s plus 6, therefore we just found out that the inverse Laplace transform of this function is 2 times e to the minus 6t. So really we want to start to look at the structure of the function capital F and try and line it up with some function that is sitting in this column over here. And then once we've identified that, we can jump over to the first column and figure out what the inverse Laplace transform would be.